If you've ever modeled 2D space with vectors before, you may have noticed that it's pretty strange. The vector multiplication is weird, and you have strange things like matrices that transform space. But if you've ever modeled 2D space with complex numbers, at least for me, it makes things a lot simpler because complex numbers are just that, numbers. But we live in 3 dimensions, and the complex numbers just aren't enough when describing 3D space. It would be very useful to have a number system that lives in 3D space. This exact problem was faced by 19th century Irish mathematician Sir William Rowan Hamilton. Hamilton was looking for ways to extend the complex numbers from 2D to 3D, but he failed to find any meaningful 3D numbers. He eventually realized that we can't use 3D numbers to extend the complex numbers because if there was a third number, it would not be defined when you multiply it by I. What he eventually discovered was 4-dimensional numbers, which used in the real numbers, the imaginary numbers, and his new numbers, the quaternions, which he described by this equation: I squared equals j squared equals k squared equals I times j times k, which is equal to -1. J and k are the new numbers here. They're also the square roots of -1. These numbers sit in 4 dimensions, so I can't show you the full space or hyperspace that they live in. These numbers are also easy to multiply together. Here's their multiplication table. But if you stare at this table long enough, you'll notice that something's up. Where did the commutative property go? The commutative property is the simple property that order doesn't matter when you're multiplying numbers. It works for the real numbers and the complex numbers. For example, 2 times 3 equals 3 times 2, and 1 plus I times 2i is equal to 2 to I times 1 plus I. But when you use quaternions, this property vanishes. For example, I times j is equal to k, but j times I is equal to -k. If you switch the order, the sign changes. And I don't know about you, but I'm starting to not like these numbers. I think we should find an alternative. Well, how do people find new numbers before? I already made a video that talked about this, but as a quick overview, what people did in the past is they found numbers that were undefined before and just defined them. For example, negative numbers and complex numbers were not defined before, but now are. So what numbers are undefined today? Well, 1 divided by 0 comes to mind, but we actually have reasons to keep that undefined. The most common one is that if you look at the graph 1 divided by x, and the limit as x goes to 0, 1 divided by x goes to positive infinity from the positive side, and goes to negative infinity from the negative side. And since a limit cannot have 2 values, that we say that this limit does not exist. But there's a slight flaw with this. A limit doesn't always have to have the same properties as the answer. Take 0.9, then 0.99, then 0.999, then go on forever. The limit is a whole number, 1. But the path is always a non-whole number. Does that mean that 1 is a non-whole number? Of course not. It's just that not everything survives the limiting process. So with that being said, maybe we just can't trust the limit. So let's assign a number to 1 divided by 0, say alpha, and let's mess around with the properties of this number. What would be, say, 2 times alpha? Well, since alpha is 1 divided by 0, 2 times 1 divided by 0 is equal to 2 divided by 0. So 2 times alpha is equal to 2 divided by 0. What about I divided by 0, or the square root of negative alpha? We have not defined that yet, so let's call it beta. Now what if we say these numbers live apart from the complex numbers? Then we can say that all of these numbers, the reals, complex, and these new numbers all combined together make a 4-dimensional number system, which is exactly what we were looking for, an extension of the complex numbers, and it has a bonus. It gives us the solution to x times 0 equals 1. And also, the inverse of alpha is 0. Now you might be wondering, is 0 divided by 0 still undefined? Well, it's just the solution to the equation 0 times x equals 0, which really can be any complex number. We'll denote it with psi, the Greek letter. You might have seen this number before. It's that annoying plus c at the end of every indefinite integral, or the constant of integration, which definition is any complex number whatsoever. How did nobody ever think of this? I don't know, but anyway, I hope you found this monumental discovery in mathematics very exciting. Thanks for watching. Just kidding, even if you did all of that, 1 divided by 0 would still be very much undefined. If you want to see why, just try to take a fraction of 1 divided by 0. It's still 1 divided by 0. And so the half of something is equal to that something, which doesn't remind me of any concepts in math I've ever heard before. I still don't like the quaternions, but instead of trying to find new numbers, I think we should use vectors for modeling the 3D world, even though they're confusing. In fact, vectors better explain things in areas like physics. For example, the Lorentz force law states that the magnetic force is equal to the charge of a moving particle times the cross product between the velocity of the particle and the magnetic field. The cross product is a way to multiply vectors together. But anyway, I hope I at least built your trust in that 1 divided by 0 is still very undefined. Thanks for watching.